Most people in this audience probably know Jeff Greason. I've known Jeff for, again, longer than I want to admit. We probably met early 90s, mid 90s, and we're still friends. Jeff has been a frequent speaker at the previous incarnations of this event, and really looking forward to his new work on wind-pellet shear sailing. So Jeff, up to you.
So let me start by thanking my collaborators who are listed here. I'm going to move rather swiftly, so I will let you read their names. But they've been a tremendous help in getting this project reduced to a presentable state. Next slide. I need to review some things that you already know, but it sets the context for where I'm going with this. Interstellar travel is fundamentally a problem because the energies involved are huge. If you want to send a no-kidding spacecraft, something that includes luxuries like a power supply and a communication system and things like that, you're talking about payloads in the hundreds of kilograms. We don't send flagship missions that are much smaller than that for good reason. If you leave some room for a propulsion system and call it, just to pick a round number, 1,000 kilograms, that's 1.8 times 10 to the 18th joules, 60 gigawatt years of kinetic energy embedded in that spacecraft, moving at 0.2% or 20% of the speed of light. Okay, big number. What's that mean? That if it was an antimatter rocket with the best efficiency we can imagine on paper you could get out of an antimatter rocket, you'd need to annihilate 120 kilograms of antihydrogen to get that velocity. You do not buy that at Radio Shack. If it was a fusion rocket with the best practical ISP that we have a hope of getting, 500,000 seconds, that would need 162,000 tons of fusion fuel. This is not a cheap mission. It's currently unavoidable with any of those strategies. Okay, this has been known for a long time. The obvious way around that is don't carry the power supply with you. Beam the energy in some fashion from the ground or from Earth orbit. Beamed momentum, those systems are thought of as beamed energy, but they're really beamed momentum. You send a photon to the ship, it bounces off, it transfers its momentum to the ship. You send a particle, it bounces off, it transfers its momentum to the ship. That absolutely loosens the limits and it makes these things within the bounds of possibility. But when you start scaling up from grams to kilograms, things start looking not so nice. The beam has to have enough range to keep the spacecraft in the beam while it's accelerating. And that means either you have to have a really high power beam so you can get a lot of acceleration done in a relatively short distance, or you have to hold the beam together over unphysically large distances. I haven't tried costing out what the beam would look like for a 1,000 kilogram target, but I can tell you we can't afford it. It's a big beam. Okay, how do you get better than that? Well, the sail beam or pellet runway or pellet propulsion concepts are a way to evade those limits. You send guided macro particles, grains of sand, puffballs, something like that. Those are macroscopic objects. They don't spread out from thermal effects in vacuum, so they can, in principle, be made to go over quite a long range. That's a big help. It still doesn't get you down to the point where 1,000 kilogram spacecraft starts looking affordable. And then the last step in this intellectual development is Jordan Kerr's idea, which, God, we miss him, which is the fusion pellet runway. Now, the advantage of that concept is you put down a trail of breadcrumbs of fusion fuel in front of the spacecraft. Okay, big advantage all of a sudden. The pellets don't have to go as fast as the spacecraft. Yay. But what that essentially is a seated Bussard ramjet. You run into the pellets, you convert their energy, and you use that to squirt out the reaction mass out the back. And just like a Bussard ramjet, you have to pay for the drag of running into the pellets. So when you start getting to large multiples of the kind of exhaust velocity you get out of a rocket, the mass of the pellet starts to skyrocket again. And it helps again, but not enough. We're still not there. Next slide. Okay. The Holy Grail for me, for the last 5 years thinking about this, has been how do we get the energy from natural sources so we don't have to buy the beam? And last year's talk was a big step forward in that. The Q drive lets you take a big spacecraft going at a reasonably fast speed and turn it into a small spacecraft going even faster. That's a big help. But it does absolutely nothing to get you the kinetic energy in the first place. It just lets you concentrate that kinetic energy in your payload. You still have to get the kinetic energy from somewhere, and it's still a big freaking number. The problem is natural sources have limits on how fast we can get the energy out. Two examples of that, both in the prior literature cited here. If you release little carbon puffballs, aerographite pellets, close to the sun, they have such low density and can take such a high temperature, they can pick up about 2% of the C leaving the sun from photon pressure. And tomorrow you're going to hear about some work from my friends at the University of Toronto that I've been helping with, not University of Toronto, I'm sorry, McGill, that talks about ways to get the solar wind energy harvested to get up to also about 2% of C. This is great. 2% of C is still not 6 or 7% of C. You still have a gap to close. Today is about how to close that gap. That does work. Okay, here's the big idea that you have to get your head around, and I'll spend the rest of the talk talking about it. If the pellets are slower than the spacecraft that's running into them, but they're also moving in the interstellar medium, so they're faster than the interstellar medium. When you run into the pellets, there's a velocity difference that you're encountering between the wind that you run into and the pellets that you run into. Now, what does that let you do? Well, it looks different if you look at it in the ship frame or if you look at it in the rest frame. In the ship frame, it looks like I ran into this wind, I can extract power from the wind, and I can push on the pellets as my reaction mass. It's like having a roadway that you roll your wheels down, or as we call it for short, a pellet cog railway, where your gears engage the pellets as you go. In the rest frame, it looks different. In the rest frame, it looks like the ship ran into the pellet and it extracted the kinetic energy of the pellet and left the pellet at rest with respect to the interstellar medium. And the kinetic energy imbalance goes into the ship. This is hard to get your head around because it's a 3-body interaction. It's not a 2-body interaction. You have the wind, the pellet, and the spacecraft. Okay, so this is the basic principle. If you look at what the energetics are of running into a matter stream, in the limit where the wind or the velocity of object 1 is heavy compared to the velocity or mass of object 2, it follows the propeller equation. The power involved goes with the thrust or drag times the velocity. So the magic answer here is if you're running into 2 matter streams and you are running into them at different speeds, you want to extract energy from the fast one and you want to push on the slow one because it takes less energy to push on the slow particles than you get out of running into the fast particles. So this is an example with numbers. I will not dwell on it because of time. But I just put nice, simple meters per second numbers in there so you can see for yourself afterwards how the numbers add up. You run into the things that going at 5 meters a second, you extract energy. You push on the things going 3 meters a second. When you're done, both the energy and momentum have balanced and you've been left with a modest amount of thrust, which appears at first to come from nowhere. But it doesn't come from nowhere. It came out of removing the kinetic energy from the pellet stream. So when you start, the pellets are moving through the wind. And when you are done, the pellets are at rest with respect to the wind. That energy goes into the ship. Okay, there is if this seems confusing to you, don't feel bad. Lots of people have been confused by this over the years. There's a little physics bet that you can find on YouTube with the links shown down below, where a real physicist lost $10,000 betting that this couldn't work. But it does work, and it is hard to get your head around because you have to keep track of all 3 parcels of mass. So I will quickly try to play that. I don't know how to play it, but oh, there we go. So this is a vehicle in which once it's going downwind, the fast thing is the ground, and the slow thing is the wind. It's going downwind. Initially, it's pushed by drag on the propeller. But if you watch the little telltale at the front of this vehicle, there's a little yaw string there at the front that's clearly pointing towards the nose because it's in a tailwind. And at some point here, it's going to start getting to the point where the telltale is pointing back at the pilot because it's going to be going downwind faster than the wind speed. There it is. It's exactly the same principle. There's two streams of mass passing the vehicle. One of them is the ground, one of them is the air. You can extract energy from that difference. That's actually also the same physics that racing hydrofoils can now use to sail downwind faster than the wind speed. Because in that case, the fast mass is the water and the slow mass is the wind speed. Okay, a little bit of equations here. This is the most simplified version of this. When you start factoring in efficiencies and finite masses, the equations get more complicated. But the analysis is easiest to do in the limiting case where the ship, you look at the rest frame. The ship's moving with the velocity of the spacecraft. It overtakes a pellet, has a certain kinetic energy. There's this mediated collision, this three-body interaction that's going on between the ship, the pellet, and the wind. And when you're done, the pellet's at rest with respect to the wind, and the spacecraft has acquired velocity moving to your right on that diagram. And when you run the equations on that, the final velocity of the spacecraft is the velocity of the pellets. And assuming you start at the same velocity as the pellets, using whatever you push the pellets up to speed with to also get your initial velocity of the spacecraft, times the square root of the ratio of the mass of the total sum of the pellets that you picked up to the ship, plus 1, which is your starting velocity appearing in the equation again. This looks a little bit like the Q-drive equation because in both cases it's conservation of kinetic energy drawn up in a slightly more complicated form. However, note that if you don't get too greedy with this stage, in other words, if your desired final velocity is not too large a multiple of your initial velocity, that mass ratio gets to be not too scary a number. You know, if you want to triple or quadruple your speed, the pellet mass is on the order of 9 or 16 times, or 8 or 15 times in this case, the initial ship mass. Okay, that's not a very scary number. Next. Okay, to turn this kind of idea into hardware, there are 3 major things that you need. Well, 4 really. You need what we're calling the pellet dispenser, the thing that lays down the runway of the pellets, harvesting natural energies to do that. You need the windmill, just like the Q-drive. You need the wind energy extraction system that you pass through the interstellar medium plasma and turn that into energy at the cost of drag. There were some options. You need the usual tricks, by say usual, that Jordan Kerr put a lot of skull sweat into on how do you aim the pellets and how do you track the pellets and how do you steer the ship so that you can run over the pellet stream. One constraint we found about that is it does mean that there's a limit to how physically small you can make the pellets because you need to be able to see them coming in time to steer the ship onto the center of the mass stream. But the solution to that turned out to be you make them very low density objects. You make them hollow, like a frozen soap bubble or an aerographite pellet or a piece of hydrogen snow, something very fluffy so that it has a nice big radar cross section when you run into it. And then you need what we're calling the pellet pusher, the thing on the spacecraft that takes the high velocity pellet coming in the spacecraft frame. You run into a pellet at high velocity and you leave it at even higher velocity. You've added energy to the pellet from the spacecraft's point of view. That turned out to be particularly challenging. There's not an awful lot of work being done on how you do ramjets at 3% of the speed of light that kick the pellets out at 5% of the speed of light. But we did find 2.5 promising avenues of approach for that. Cross-field accelerator and MHD type of accelerator. In that case, you have to heat up the incoming pellet hot enough to be a conductive plasma. That's not very hot. And then use J cross B forces to push it out the back. A linear macroparticle accelerator, basically a dust grain accelerator of electrostatic type. And we're still going back and forth on whether or not a thermal type of approach is possible. If it is, it involves a very, very hot plasma. but I include it on the list because there's some future work where that might turn out to be relevant. I'll move through quickly a conceptual example of what this means for the mission. I'm looking at a 500 kilogram payload and just by arbitrarily, because obviously there's no engineering analysis here, but I have to do something to do the numbers. I've set the dry mass of each stage equal to its payload. You know, that's probably not of the wrong number of orders of magnitude, but it's by no means closer than I guess. There's a Q drive second stage that gets you from just over 5% of the speed of light up 20% of the speed of light. We use 2% of C pellets, and we use that to push the whole stack up to about 5.5% of the speed of light. What does that get you? I'll cut to the bottom line. What that gets you is for your 1,000 kilograms of mass that ended up in Alpha Centauri orbit, because you can use the Q drive also as your brake at the other end. You needed a total launch mass of about 300,000 kilograms, or to put it another way, 3 Starship flights. Okay, that is by today's standards, that's a big mission. That's actually slightly larger than one Apollo Saturn V stack. But it's of the same number of zeros as an Apollo out of Saturn V stack. And you know, first you launch the pellet dispenser in the ship. The ship goes out to the outer solar system that starts building up velocity. The dispenser goes into the sun and gets ready to start dispensing pellets. A year later, you start laying down the runway. A year and a half after that, the ship leaves the heliopause towards Alpha Centauri and starts picking up the runway. A couple of years after that, you're up at 5% of the C. You dump your first stage. Now you're on the Q drive. It takes about 4 years for the Q drive to get you up to 20% C. About 26 years after mission launch, you start braking. It takes about a year to brake. About 27 years after launch, you're in Alpha Centauri orbit. And about 4 years after that, you get your data back. This is kind of following the structure that Mark Millis was talking about for how we compare performance of missions. 30 years is short enough time that the principal investigator of the project can still be alive to collect the Nobel Prize. You know, saying what technologies you haven't matured yet cost is a silly thing to do. But you can certainly look at what the absolute minimum it can cost is, which is the mass, the cost to launch all this stuff. Today, at today's launch prices, that's $600 million for launch cost. And I don't mean, that's not Starship, that's Falcon. And almost all this mass is the pellet mass. It's just inert mass that you're going to form into the pellets. It's not big, complicated spacecraft hardware. So there's no reason that can't go up on more than one launch. At a credible future scaling, it's not crazy to think that when we start doing things like mining lunar materials, we can get the cost of bulk mass down to $100 a kilogram. That would make the propellant cost for this mission on the order of $30 million for 1,000 kilograms, which is sufficiently cheap that thinking about scaling this up further to a human scale mission is not completely crazy, which is the first time I've been able to say that since I started looking at this field. And other options are very hard to cost also because they have their own technology gaps. So let me just say, this looks like it's got a different number of orders of magnitude in the cost number than any of the other alternatives I know about. Lots more to do. We need to take all of these elements to a much greater level of detail. This is all at the conceptual, how did the physics work level. The internal power flows of the vehicle can get very big, which is going to put a premium on either operating at a very high temperature so the radiator mass doesn't get crazy, or operating in a superconducting regime so the amount of waste heat that you have to manage is very small. It is interesting to consider marrying this idea and the fusion pellet runway. There's no reason why you have to run over inert mass. You could run over mass that's contributing its own energy to the problem, and that would be interesting to look at further. And I want to put a special thanks to the TVIW conference, which brought all the authors of this paper together to start this collaboration. So, you know, it's doing what it's supposed to do. And also to Matterbeam, who asked me the right question at the right time to help me get over a conceptual problem. And if there is any time left for questions, I will take them.
Thank you, Jeff. Yeah, we have time for a question. How far are the pellets spaced from each other?
Right now, the conceptual design maxes at 100 hertz of 0.01 seconds per running into them. In practice, that's thousands of kilometers apart from each other because you're moving really freaking fast. But a related question that we didn't get into is how long is the runway? And the answer to that is thousands of astronomical units. You launch pellets at 2% of the speed of light for years, and then you hoover up that runway as you're following it along. And with that being the one question, thank you, and I'll be around if there are more during the breaks.
Thank you, Jeff.